So this particular segment is about periodic table. It's the first lecture in Unit 9, and we need to spend a little bit of time talking about the periodic table and how it works. The first thing that we need to discuss, though, is the idea of what a valence electron is. So a valence electron are the electrons that are in the outermost energy level or the outermost shell of an atom. So here I have an atom that has 1, 2, 3 total electrons, but there's only one electron in the outermost energy level, so this one will have one valence electron. Whereas this particular atom over here on the right hand side has 1, 2, 3, 4, 5, 6, 7, 8, 9 total electrons, but in the outer shell it has 1, 2, 3, 4, 5, 6, 7 total electrons. So this one has 7 valence electrons. And by looking at this, I can identify where these atoms are on the periodic table, but we'll talk about that in a minute. So there are special groups on the periodic table, and this is a diagram of the periodic table that has Bohr models drawn out for the first 3 periods or the first 3 rows. Period 1, 2, 3. So in group 1, what I would like you to notice is that every single atom in group 1 has 1 electron in its outermost energy level. So on your periodic table, on the back of your packet, I would like you to, above or below period 1 or group 1, to write 1 valence electron, because everything in that column, in this column right here, all the way down, is going to have 1 valence electron. And if you take a look at group 2, every single element in group 2 is going to have 2 valence electrons. So everything here will have 2 valence electrons as well. We're going to skip the ones in the middle. So we're going to skip these elements here, elements in 3 through 12, and we're going to go to group 13. And there's a reason for that, and we'll talk about that at another point in time. But for now, if we're looking at this column right here, you should note that these all have 1, 2, 3, and 1, 2, 3 valence electrons. So this column has 3 valence electrons, which brings me up to group 14, which has each atom has a grand total of 4 valence electrons here. Okay, and then group 15 will have something like, let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this one will have 5 valence electrons. And group 16 will have something like, over here, oops, we want that to be this color. So this one will be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 valence electrons. And then group 17 will have a color will have 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, 6, 7. So 7 valence electrons. And then lastly, group 18 is a very, very special group, and that very, very special group is going to be having a grand total of, it depends. So neon will have 8 valence electrons, so will argon. So we would generally say that these are going to have 8 valence electrons. There is an exception with helium, and that'll have 2 valence electrons. We'll talk about that at another point in time. So, each column on the periodic table has a special name, and we don't need to know all of them, but we just need to know some of them. So the very, very first group, this group right here on the periodic table, okay, is called the alkali metals. They all have one valence electron, and they are incredibly reactive. That means they're willing to give up their valence electron and become a positive ion. So in each of these, so all of the elements in this column here, every single one of them was willing, very willing, to give up its electron. So we call those the alkali metals. Groups 2, 3, 13, 14, 15, and 16, they have special names, but they're not that important. But the outermost electron shell is partially full, so they can be reactive. So this one is 2 valence electrons, 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons, 7. We got a little carried away, so we only really need to go to 6. So that's that. And now group 17 has another special name. We call it the halogens. And so everything in this column right here, they all have 7 valence electrons. And they are also incredibly reactive. They're incredibly reactive because they need one more electron. So these guys are very, very willing to accept one more electron. And when they do that, they become a negative ion and they become a little bit more stable. The last special group that we need to talk about on the periodic table is column 18. It is the noble gases, and they're called the noble gases because they have a full octet, or their outer ring is completely full. So like neon has the 8 valence electrons, and so does argon, and so does krypton and xenon and radon, but helium only has 2 valence electrons, but that's okay. That makes it a noble gas because, again, its outermost electron shell is full, and that's the important part. Now, the octet rule is a rule in science and in chemistry that allows us to kind of sort of decide what's going to happen to an atom. Is it going to gain electrons? Is it going to lose electrons? We can follow this rule a little bit. So the octet rule basically says that atoms tend to lose or gain electrons, so they will end up with an outermost energy level that's full to a capacity. Generally speaking, atoms want to have 8 valence electrons. That's the goal. So if we're looking at this particular atom right here in front of us, we have one that has 1, 2, 3, 4, 5, 6, 7, 8. So in this case, this particular atom already has 8 valence electrons, so it's full. The octet rule is satisfied. If by chance it didn't have 8 valence electrons, so let's pretend that in this case here, we covered up this electron. What this particular atom would do is it would attract an electron to it, so like, and when it attracts an electron to it, it would end up with that 8 valence electrons, and then it would be more satisfied. And that's exactly what these atoms want to do. But, so, the Bohr model we have to review from a long time ago. We have to review a couple of things. The first energy level can hold 2 electrons. This guy holds 2 electrons. The second energy level can hold 8 electrons. This guy holds 8 electrons. And the third energy level can hold 18, but it's stable at 8, and we're going to kind of try to focus on it being stable at 8. So when you draw these structures, which you're going to have to do for homework, you're going to have to make sure that you're following those rules. Now, ions we have to review a little bit. A neutral atom of hydrogen will have protons, neutrons, and electrons. 1 proton, 1 electron in a neutral atom, so it will look something like this guy right here. Whereas a positive hydrogen ion will have a proton, and it will have an electron, but the electron is gone, so what that means is that this 1 electron here left the atom, and we get a positively charged ion. And in a negatively charged hydrogen atom, we have protons, neutrons, and electrons. So we have 1 proton, and we have 0 neutrons, as these do. And the electrons in this case started with 1, but an electron was added, so it ended up with 2 electrons. So in this case, we have 2 electrons here, so its overall charge is going to be a -2, or a -1. So this is a -1, this is a +1, and this has a neutral charge. So let's draw a Bohr model for fluorine, okay? Fluorine 19. Couple things to remember, that the number on top is the mass number, and the number on the bottom is the atomic number. Oh boy. The atomic number tells me the number of protons. The mass number tells me something else, so we're going to talk about that in a second. So in this case, we know that we have 9 protons. It's a neutral atom, so it's going to have 9 electrons. And then the neutrons is mass number minus atomic number. So it'll be 19 minus 9 for 10. So when I draw this structure inside my nucleus, I'm going to have 9 protons, and I'm going to have 10 neutrons, and in terms of electrons, I'm going to have 9. So the first circle can hold 2, that's the first energy level. The second energy level can hold a total of 8. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So in this case, I don't have to go into the third energy level, but I've drawn this structure so that I can see that it has 7 valence electrons. Okay? So this guy has 7 valence electrons. It wants to have 8 valence electrons, so it's more likely that this atom, this neutral atom of fluorine, is going to want to gain an electron. Looking like this. If I were to draw an ion that forms with fluorine, again, this is the mass number, this is the atomic number, which tells me the number of protons. So I know that I have 9 protons, okay? And we said that this is mass number minus atomic number. So that's going to be 19 minus 9, which is 10. And now this case, so I need to go back and look at this. So let me just kind of draw what we have first of all before we start talking about electrons. So in this case, I have 9 protons and 10 neutrons, and I'm going to draw the original 1, 2, 3, 4, 5, 6, 7, 8, 9. So it has 7 valence electrons the way that it is, and the most likely ion, based on what we talked about, is it's going to grab an electron and want to attract it. Oops, I went a little too far. Grab an electron, and it's going to want to attract it right here. And when it does that, it started with 9 electrons, and we added 1 electron. So now it has a grand total of 10 electrons. So those 10 electrons now give this a charge. And as a result of that, I have more, so protons plus 10 electrons will equal an overall charge of -1. So in this case, I know that fluorine's charge is going to be a -1, which is what we have down here. Okay, so that sort of sums up this particular video. Your homework for the evening is to complete worksheet 1, which is about the periodic table. It's going to be drawing a lot of Bohr models as the original structure and the ion structure looking like that. So we'll go through that in homework in class tomorrow.